You guys had me wondering for a little bit if I was here on the wrong day or something, because it was just me here alone. No worries. Everyone's waiting till the very last minute. I don't blame you. Yeah, cat things get in the way. Just waking up things get in the way. That's fine. That is totally fine. All right, so good morning, happy Tuesday. Here we go. So for a little bit of review, I'm upset with myself that I don't have more examples like this one, right? So we ended off here. We talked about well, we talked about lots of things, but we kind of ended up talking about sets and intervals. And usually there's a question very similar to this one on test one and also on the final. So that's why I'm kind of, in hindsight, I'm kind of surprised I only put essentially one of these on here. But let's work on this one again. It's been a while, so maybe we don't quite remember anyways. All right, so we talked about sets and intervals and lots of fun stuff last day. Get this set up here. I'm sure you have kind of organizing things to do on your end too, so get situated. Okay. So it looks good. It looks like I've got, last time I checked, I have 8 people in WebAssign, so that's really great. Nice work. If you're having trouble, I posted, kind of jumping around here, but I posted on our Moodle page, and hopefully it makes sense. I made a little WebAssign section here. Kind of the link to where you can buy the textbook later. But remember, we have that free trial until I want to say the 26th. So just use the free trial until you know for sure you're staying in the course. And I was kind of, I wasn't able to do it on my own. So if these steps are a little bit incorrect, then I'm sorry. But the general idea is you have to go to the login page. You either have an account or you have to create an account. If you've used WebAssign before, then you have an account. Awesome. Okay. So they are correct. That is good news, because I used it for a different course too. And then you're going to enter the class key, which is that kind of funny looking thing. And I've got a screenshot of what it should look like when you get there. So, so make sure you get in there to see the assignments. You've got a couple of assignments. I think I made some due on Friday this week. So definitely the getting started with WebAssign is probably, if I know myself, it's probably due on Friday. So make sure you can log in to our WebAssign, as we have assignments. I'm pretty sure I bumped them. We have assignments due on Friday. All right. And let me just, why not? I'll go there. Come on. There. Let's have a look just to see here. We've got assignments. Yeah, getting started, and the assignment for section 1.1 is due on Friday. Good. And it looks like I've got 8 people in there. So that is really good. The getting started and section 1.1. Okay. So quick review, but then we'll do an example as part of our review. So review, what did we do before the sets? That's what I want to know. Let me just refresh my memory here. Oh yeah, we dealt with fractions, negatives and fractions. Negatives and fractions, right? For fractions, and we're going to come back to fractions, so that's why I'm not going to review them that much. We'll come back to them and do a lot of fractions in, I want to say 1.3, so don't worry, they come back. They come back to haunt us. But the main idea was we need a common denominator to add or subtract fractions. And then we talked about sets and intervals. Right, for sets, we did introduce some weird notation. We used the intersection. The intersection, which you can read as and. Right, and I like to just kind of, it's an upside down U, but if you put a line, if you draw a line through here, it looks like an A, right, a capital A. And so that's how I remember that that's and. And then the normal U is the union, which you can read as or. Right? So and or. All right, so we'll do this example for part of our review. Now, remember we talked about set builder notation, and I kind of said, okay, well, I'm not going to use set builder notation so much, but I need you to be able to read set builder notation, right? And so sets are enclosed in curly brackets, and sets are just sets of numbers, right? And so numbers that satisfy some properties. So how you're going to read this, and I'll zoom in here, is, so A is the set of all x's, and then this vertical line is such that, and we talked about this last day, so that's why I'm not writing it down, but x, so such that x is greater than or equal to -2. Okay, so all the numbers, so any x that satisfies this criteria, x being greater than or equal to -2, is in the set A. Whereas for B is the set of all x's such that x is less than 4. So we need to keep track of those inequalities, right? Less than, greater than, less than or equal to, greater than or equal to, right? And so here we're excluding 4, and here we're including -2. So there's a lot going on here. And then we can do something even kind of more advanced. We can say, okay, x is between -1 and 5, not including -1, but including 5, right? And so what we have to do if we want to find B union C, so B or C is how you would read this, right? Or if you want to say union, that's totally fine. But if it has to be in B or C, that's kind of helpful when we figure out, okay, what numbers are we talking about here? So it can be either in the set B, where x is less than 4, or it can be in the set C, where x is between -1 and 5. So what I like to do when I set these problems up is I like to draw all these intervals, right? I need to draw all these intervals on a number line. And then I can see where they overlap. I can see where they kind of extend beyond each other. Okay, so I'm going to use different colors here. I'll do A in green, and then I'll do a line for B, and then I'll do a line for C. Okay. And then I'll do my number line down here, and I'm going to use lots of space here, but that's okay. Instead of just kind of blindly drawing a number line, it's not so important that you have the spacing all correct, right? It's more to visualize these sets, but you need to figure out kind of, oops, switched, what cutoff points you need to put on this number line, right? So we're going to be talking about -2, 4, -1, and 5, right? And so I'll probably just put 0 in the middle just for some sort of reference point. You don't have to, because we don't actually talk about 0 explicitly, but then I'm going to have -1, -2, -3. Then I'll have 1, 2, 3, 4, 5. Like I said, you can go you don't have to have proper spacing, but in this case we were able to, so why not? Doesn't hurt. So what I'm going to do is I'm going to draw each of these sets on an interval. And so what we need to remember is that sets and intervals and inequalities, they're all the same, right? They're just different ways of showing the same thing, right? So if x is greater than or equal to -2, right? First thing I'm going to notice is that it's including that endpoint of -2. So for my A line, I'm going to be here and I'm going to include -2, right? So I'd show that by doing a closed dot. Right? And then I go back here and I say, okay, x has to be greater than or equal to -2. Remember that trick where if you make an L with your left hand, right? If you can read it like this, x is less than, well, in this case, it's facing the other way, so it has to be greater than, right? X is greater than or equal to -2. So to show that, what I'm going to do is I'm just going to extend this line and just show that it keeps going, and it keeps going for all x's that are greater than or equal to -2. I do the same thing for B. Right? X is less than 4, not including 4. So what I have to do is I have to do an open dot here at 4. And then x is less than 4, so all x's that are less than 4, and it just keeps going and going and going and going. Okay. And then for my last set, I don't include -1, but I do include 5. So what I'm going to do, I'm going to start, and I'm not including -1, but I am including 5. Okay. So then I can connect these because the x's are all the values between these 2 points. Okay. So I can't actually remember which ones we did or didn't do. So 45A, if we want B or C, so I usually read it as B or C because that highlights to me that it can be in either B, right, or C. It doesn't actually matter. So the kind of the joint area that we have here is starting at 5, and then it's going down, down, down to -1, but then here it picks up again. And so here, B or C, or B union C, is going to be all values that are less than or equal to 5, right? And I'm going to use interval notation. Remember, interval notation is when we use the square or the round brackets, and kind of reading from smallest value, from -infinity In C, it is a closed dot at 5 because it's including 5. Is that the one? I mean, cool. So we're starting here at the far right, okay? But when we write our interval, we start at negative infinity and we go up to 5, including 5. So how I usually denote our intervals is with interval notation, right? In set builder notation, what would this look like? Right? Or the set of all x's such that x is less than or equal to 5. Right? If you had to use set builder notation. So you need to be kind of fluent in moving between interval notation and set builder notation, right? But like I said, I'm not going to make you create set builder notation, but I do need you to be able to read it. Right? So let's do B here, B and C. So now the values in my set B and C, or B intersection C, has to satisfy both B and C, right? And so looking at B here and C, right? B, well, I can't have all the what values from negative infinity up to -1 because they're not in both sets. So what I do is I pick up here at -1, not including -1, right? So what I can do is I can start and I can say from -1, not including -1. So that's when we use that round bracket. And then here I've got overlap, overlap, overlap. So it's all good. And then it ends here at 4, right? So not including 4. So I do a round bracket. Or if you're trying to practice your set builder notation, right, the set of x such that, and then I'm going to put x in the middle here. X is greater than -1, but less than 4. Okay. Just for lots and lots of practice here, let's do 46 as well. But moving a little bit faster this time, right? Because we've already seen the intersections and it's intersections in both. So it's the overlap. 46A is A and C. Okay. So it has to satisfy A and C at the same time. So this little section between -2 and -1 is not valid because it's not overlapping, right? We pick up here at -1 and then overlapping, overlapping with A and C. Make sure you're looking at the right lines. And then it's closed dot here at 5, right? That is the same as C, right? And so we're still going to just say it's from -1 up to 5 and including 5, right? And just recognizing that, okay, well, that is the set C, so you can just use that notation, right, for your set builder. B, A and B. Now I'm looking at the overlap. So here I'm picking up at -2, including -2, and then I drop off at 4, not including 4. Including -2, I think. Yeah, and then excluding 4. So that's kind of the end of our review. I'll keep it on the same page there. Good. So I haven't seen any questions besides the open dot earlier. So we'll keep going. But if you do have questions, let me know in the chat or however you want. But otherwise, let's talk about absolute value and the absolute value function. Okay. So the absolute value we use we use to kind of say, okay, well, I want this value, but I need it to be positive, right? So we use the absolute value to make values positive. We use the absolute value function, or I'll just say we're not introducing oh yeah, so the open dot means it's not including -1, for example, here. And then the closed dot is when it's including 5. So this would be, right, an open dot because it's not including -1. And here it's a closed dot because it is including 5. Right? And in terms of your interval notation, right, C, you could write as -1 up to 5. Awesome. So there's kind of 3 ways to bake a pie. No, 3 ways to have the same information. Awesome. So we use the absolute value to kind of turn the negative values into positive, to make values, and I'll just kind of put make in quotes. We don't really make values, but we use the absolute value to make values positive. Okay, so what it looks like is this. So the absolute value we denote by these vertical lines around some number or some variable. So these vertical lines around a number indicate, oh, that didn't look very good, did it? Not much better, but so vertical lines around a number indicate the absolute value. Okay, and the absolute value says you're just going to drop a negative. If it's negative, you're going to drop it. Technically, what's going on here is, okay, if A is positive, right, then you just return A. Whereas if A is negative, then you take the negative of that negative number, which makes it positive. And that's what we talked about last day, right? Properties of negative. If you take a negative of a negative, it returns a positive. So here, I'll just kind of make a note here. Taking the negative of a negative makes a positive. Okay. So things like, let's see if I have any. Oh no, I stuck to the problems that we need to be able to solve, but that's okay. For example, if I want the absolute value of 73, the absolute value of 73 is just going to be 73. The absolute value of -73. And now the value inside is negative, so I'm going to take negative 73. Or if it's easier, you can just think I have to drop the negative, right? And so the absolute value of -73 is also 73. And there are properties of the absolute values. We're not going to do too much with absolute values, but let's just bring them in just for kind of completeness sake. Okay. So the absolute value of a number is always going to return a positive number, right? And the absolute value of so if the negative is outside, right? So here, good question. Versus if you have negative absolute value of 73, that's going to be negative, right? It's the negative of 73. In fact, let's just make this negative inside here just for an extra little twist, right? This absolute value of negative 73 just turns into 73, but then you've got the negative on the outside that you need to retain. So that negative sticks around. That's a great question. Good. And I think it's on one of the assignments, so it might be worth making a note on that one. So you have to be really careful. If the negative is inside, it kind of disappears. But if it's on the outside, it sticks around. Okay? So what we've seen up here is that the absolute value of A is the same as the absolute value of negative A. We are allowed to split up the absolute value if we're multiplying, right? It only works if we're multiplying or dividing, okay? If we're adding and we've got this kind of situation, now I don't want you to worry too much about this, right? We're going to deal with absolute values as they come up, but I'm going to say don't worry about property number 5 for now. Okay, because it can be kind of confusing. So what it's saying is that if you've got A plus B inside absolute value brackets, all it's saying is that it's less than or equal to the absolute value of A plus the absolute value of B. So we don't have this equality like we do in multiplication and division. We have this inequality, and you can try it with different numbers, right? But like I said, we're going to kind of parking lot that for a little bit. Okay. So how I test the absolute value is kind of a useful thing. It's the distance between points on a real line. So in order to find the distance, right, if you're thinking about the distance between -2 and 3, right, in order to do that, you would have to say, okay, or you would probably say, okay, from -2 to 0, I've got a distance of 2, and then from 0 to 3, I've got a distance of 3, so my total distance would be 5, right? That can be a little bit tedious, especially if I'm asking you things like, what's the distance between -141 and 274, something weird like that, right? And so what we have is this property, the distance between points on the real line, says that, okay, if you're finding the distance, just denoted by a lowercase d, and then in brackets between A and B, what we do, so A is the lower value and B is the upper value, right? If you're on your number line, A is the leftmost value and B is the rightmost value, then the distance is going to be the absolute value of B minus A. Right? So let's bring this guy in. So here, D is the distance, and AB, A is the leftmost value. Is that a word? It is now. The leftmost value on the number line. And this is the rightmost value. Okay, it has to be that, because then when we take b, well, b has to be the rightmost value, and then minus a. So you're taking potentially a positive number. It could be negative too, it doesn't matter. And then minus the leftmost value, which could be a negative number. So for example, right, if we have the distance, so here I'll put 0. So if we've got between -2 and 3, right, we know that the distance should be 5, right? So here, this distance is 5, right? Just so we can have something to kind of look at and make sure that we're doing this correctly, right? So now what I can do is I can say, okay, well, the distance between 3 and -2, sorry, I wrote that wrong. I was already in the calculation stage. -2 and 3 from left to right. Here I'm making a huge deal about it over here, and then I go and flub it. Oh well. The distance between -2 and 3 is going to be the absolute value of 3 minus, and then I put brackets around that -2 just to make sure that I don't forget that there's a negative on the 2, right? So I have b minus a, 3 minus -2. Okay? And to keep it on the same line here, I'm going to go across. Not ideal, but so here it's the absolute value of 3 plus 2, properties of negatives, right? If I'm subtracting a negative number, I'm adding it, which is going to be 5, right? Which jives with what we just said, right? The distance is 5. Okay? So usually on test 1, but also on the final exam, I have these 2 types of questions. So something like this, right? And then just to make sure that we're okay with dealing with negatives and absolute values, I have a distance between the points on the line question as well. Right? So let's do some examples here. Okay. So here, right, we're given a couple of values. Now, I trust that you'll be able to do it when you just have the number line here. So what I want to do is I want to do something like, let's do 75b and c. Because that way we also get some practice with these fractions. Right? I'm gonna have to subtract fractions. So there's a lot of components here that we get to practice. So that's a gold mine for someone on my end, right? You get to check that you make that you know how to do all these things. So let's say 75b, I want the distance. So what I'm going to do, find the distance between the given numbers, the distance between -3 and 21. So I'm going to denote that by a lowercase d, and then in the brackets, I'm going to do -3, 21. And from our formula here, we know that that's the absolute value of b minus a, where b is 21 in this case. So it's the absolute value of 21 minus -3. I guess for this first one, what I should have done is I should have done the general equation first, just so that we have it on the same page. So I'm going to just bump that down and do the distance between b. Why do I keep doing that? A and b is the absolute value of b minus a. There. Filling in our values for a and b here. right? We can do our calculation. 21 plus 3, which is the absolute value of 24. Of course, if you just wanted to go straight to 24, that's fine. Notice that we're doing the absolute value, and the reason for that is because distances have to be positive, right? We can't have negative distances. So just keep that in mind, right? You have to take that absolute value and it just drops the negative. Oops. Now I've got fractions, 11 over 8 and negative 3 over 10. Notice that this negative 3 over 10 is actually more to the left, right? And 11 over 8 is positive. So here we've got a positive and a negative. And so I'll write those down. 11 over 8 and negative 3 over 10. So I want to find the distance between, I keep doing that, AB, keep writing BA. And that D should be cozied up against the bracket. So the distance between A and B is the absolute value between B minus A. Man, I can't talk today. Bad when it's my job to talk. So B in this case is going to be the 11 over 8 and A is going to be the negative 3 over 10. So what I'm going to do is I'm going to write this out as negative 3 over 10 up to 11 over 8, which is the absolute value. And I'm going to span 2 lines here just to make it nice and legible. 11 over 8 minus negative 3 over 10. So I'm going to simplify in here first. And then remember, I have to find a common denominator. So I need to find a common denominator. And I just use the easiest one. It's not the fanciest one, but I'm just going to use 8 times 10, 80, right? Then I'll let my calculator do the work. So the absolute value of 11 over 8 plus 3 over 10, right? So here, in adding fractions, I'm just going to make a note because we haven't done a ton of them. We need to find the common denominator. We need the common denominator. So in this case, the common denominator, right, I'm going to make it be 8 times 10. And usually I just multiply across. Even if I have more than one or more than 2 fractions rather, you can just multiply the denominators and then that can be your common denominator. Like I said, it's not the fanciest way, but it is the, it's foolproof. So even I can handle it. The absolute value, so I have to keep these absolute value brackets around, but what I'm going to do, remember our trick was to multiply by 1. So in order to get this over 80 instead of just 8, I have to multiply 8 by 10, but I can't just multiply 8 by 10 without manipulating the numerator as well, right? So I need to multiply this this numerator by 10 as well. So I multiply by 10 over 10, and then kind of similarly, over on this fraction, 3 over 10, I'm going to multiply by 8 over 8. Right? And so I'm going to show that with a different color. So I get 11 over 8, and then times 10 over 10, plus 3 over 10, times 8 over 8. If this isn't quite sticking yet, you need to do more practice with these fractions. Definitely before we head into chapter 2, but even for the rest of chapter 1, we're going to be using these fractions a lot. And so just work on finding that common denominator and make sure that what we're doing here makes sense. And then the rest of the course, I dare say, will be just so much easier, right? Because we're going to be doing this a lot. Okay? Multiplying fractions, right? I can just multiply across. So what I get here, keeping those absolute value brackets on the outside, 11 times 10 should be 110, but considering I can't even speak properly, I should check that. No shame in checking things. You don't want to be doing it wrong. 8 times 10, I'm feeling confident, is 80 because that's what I'm forcing it to be. 3 times 8 is 24 over 80. Okay. Now that I have this common denominator, right, 80 and 80, that will be my denominator of my overall fraction, right? So when I combine these, I can add the numerators, but the denominator stays the common denominator. So what I have is this becomes the absolute value of 110 plus 24 over 80. 110 plus 24 is 134 divided by 80, just to see it doesn't simplify it to anything nice. So this is the absolute value of 134 over 80. There are no negatives here, right? So once we figure out that there are no negatives, then I can kind of just dissolve the absolute value brackets. And because I've got a page break here, what I'm going to do is I'm just going to erase those because, and I'll just rewrite it closer to my equal sign here, 134 over 80. So then the distance is 134 over 80. This is the exact value, and most often that's what I want it in, right? The exact value, 134 over 80. You don't have to simplify. It does simplify down, but to 67 over 40, you don't have to do that. I only know that because my calculator does it for me, right? So the key thing here is just finding that common denominator and forcing it. Okay. Good. So make sure that you do all of these just to make sure that you're doing it right, right? And remember, you've got those solutions on Moodle as well. Right, to all the problems that are in our notes, there are solutions on Moodle. And sometimes there are solutions once we get into, I posted all the notes for chapter 1 because I got those all cleaned up. And I'll post for the rest of the chapters later. All right, so that is section 1.1. So what I'm gonna do is, I guess we can, I'm trying to be better about giving you guys breaks. So how about we take a 10-minute break here, and then we'll come back and we'll talk about exponents. How about that? So I'll just make a note here. 10-minute break. Back at 8:55. Sounds good. I want to say. Good. So I'll pause this. We're back. So I'll remove this because we don't need it anymore. So section 1.2, if you've had a look at the notes, is called Exponents and Radicals. Exponents and radicals. And just to clarify, right, so exponents are powers, right? We usually say, 4 to the power of 3, for example, right? That would be an exponent. And radicals, just to clarify, are roots. Okay? So just to kind of clarify some of that terminology that we're using. So let's start by just kind of showing what an exponent is. Uh-oh, you guys might get another break here. The dog is radicals. Sounds way better than roots. I know, it's catchy, right? So we'll see if she settles back down. Radicals. Now I'm not going to be able to say it any other way. Radical. So if you have something a times a times a times a n times, then how you would write that is a to the power of n. And if you have a to the power of n, wow, the base is a, right? So you have to, and that doesn't look like an n, does it? And the power slash the exponent, right? They're the same thing, is the n. Okay, and it just means you have a times a times a times a n times, right? So let's see here. Some things to keep in mind, right? And just kind of put it in your memory bank, okay, is anything to the power of 0 is going to be 1. Okay, so that's just something to remember here. Anything to the power of 0 is 1. Okay. You might be tempted to do, 4 to the power of 0 is 0, but it's not, it's 1. Okay. If you have a negative exponent, what that's actually telling you is that, okay, well, then it belongs in the denominator, right? And so notice this relationship here, a to the negative n, it becomes 1 over a to the n, right? And so this negative just puts it down in the denominator. So a negative exponent moves the base and the power, moves the base and power to the denominator. Okay. We also use it in the reverse, right? We also use the fact that a to the negative n can be rewritten as 1 over a to the power of n, right? To simplify powers, or to simplify exponents. To simplify exponents. Okay. For example, okay, and maybe I'm jumping in a little bit too fast, so maybe I'll hold off a little bit. To simplify exponents, right? Because we can use this fact to move a to the power of n from the denominator up to the numerator. And I jumped ahead trying to do an example quite yet, but we will be doing lots of examples. So because then if I'm able to rewrite something from the denominator upstairs in the numerator, so to speak, like here, then I can kind of work with these exponents a little bit easier. So, so we use this fact a lot. Okay? So we also use the fact that we can move from the denominator up to the numerator, so to speak, to simplify exponents. And I'll keep going here because that was kind of an empty statement. By moving powers from the denominator up to the numerator by making them negative. Okay. So that's something that we're going to use a lot, especially to simplify kind of big expressions. And just a heads up, right? This is the type of problem that, you know, test one, final exam, definitely on there, making sure that you know how to manipulate exponents. So let's take a look at the laws of exponents. This is a big kind of index card, so to speak, right? There's a lot of information on here. In fact, it's gonna have to go on its own page here. Okay, but you need to memorize, or, you know, however you want to do it. All of these rules need to be intuitive, right? So they need to be, you need to be fluent in the laws of exponents. In fact, maybe that's what I'll write here to fill this space. We need to be fluent, just to kind of like emphasize that all these rules need to be just kind of ingrained in your mind. And however you want to do that, or however you can do that, do it. So we need to be fluent in the laws of exponents, which are these. Okay. Paying attention to the base, right? Here, the base is the same. So first thing you're going to do is you're going to check the base. Okay, if you have the same base, then a to the power of m times a to the power of n, you can add those powers to simplify them. Okay, so here you have to have the same base. So for law number one, my one note that I'm going to make here is we must have the same base. We must have the same base. Okay. Notice, of course, we can go the other direction as well, right? So if I have a to the power of 40, I can break that up as a to the power of 36 plus 4, right? So if I need to break it out, okay, so notice we can also use the property, and that goes for all the properties. We can also use these properties in reverse. Right? Oh, that doesn't really look like reverse, does it? There. Okay, so what I mean by that is if you have a to the power, let's do something simpler, right? A to the power of 5, right? A to the power of 5, well, 5, I can rewrite as a to the power of 3 plus 2, right? Or 2 plus 3 if I want to, 1 plus 4, it doesn't matter, right? So this becomes the same as a to the power of 3 plus 2, for example, which I can rewrite as a to the power of 3 times a to the power of 2, right? Now I have an a to the power of 2, for example, that I can play with if that's what I need. So we need to be really, like I said, fluent in using these properties and saying, okay, well, because if I'm multiplying two bases, right, then I add the exponents, okay, I can move the other direction as well. Right? Let's talk about property number 2, or law number 2, okay? A to the power of m over a to the power of n. Now, I wish it was that we had easier names for these exponents. M and n is really hard, but you can see it here. So let's talk about property number 2. Property number 2, a to the power of m over a to the power of n. Shorthand, right? If you're dividing the same base, then you subtract the exponents. Now, let's talk about why that is. We already know why that is, and if you kind of think back to here, right? If you have a power in the denominator, you can move it up, right, and make it negative. So let's talk about property number 2. A to the power of m over a to the power of n. Recall, we can rewrite this as a to the negative n, right, in the numerator. Okay, so what does that become? Well, it becomes, so then a to the power of m over a to the power of n is the same thing as a to the power of m times a to the negative n. Now, this is essentially law number 1. Again, right, I'm multiplying the same base, and so I add these exponents. Right, so here, this is law number 1. Back to law number 1. Okay. So this becomes, you can kind of consolidate that base, a, becomes a to the power of m plus negative n, which becomes a to the power of m minus n. Right, so knowing how to kind of move back and forth is going to be really useful. Okay. Let's have a look at property number 3. So if you have exponents, so an exponent on an exponent, you're just multiplying those guys, right? So here you can essentially just dissolve the brackets, but this is going to be really useful moving the other way again, right? So usually if you can break up something like a to the power of 6, a to the power of 2 times 3, right? 6 is 2 times 3, or 6 times 1, or whatever. Usually that's times 1 is not very useful, but right, so if you want to extract an a squared, so a to the power of 2, you could rewrite a to the power of 2 times 3 as a to the power of 2 times 3. Okay, and so here, property number 3, a to the power of m to the power of n is a to the mn, right? Oh, really? The dogs just go nuts this morning. So chatty. So we often use this in reverse. Right? For example, if you have a to the power of 6, you can rewrite that as a to the power of 3 times 2, which is going to be the same as a to the power of 2. Let's say you wanted to pull out an a to the power of 2. Order doesn't matter in multiplication, right? A to the power of 2 times 3. Okay. Fourth property is really just kind of a little bit of an extension, right? But now you've got a times b inside the brackets, and it's all to the power of n. And 4 and 5 go together because multiplication and division go hand in hand, right? And so you're able to bring in this exponent on the inside, but probably more common is to kind of consolidate the base. If you have the same power, right, you can smush them all together and multiply them together, or divide them depending on kind of the situation. So you can extract that exponent to the outside in either situation, moving kind of in the reverse again. So 4 and 5 say that we can expand the exponent. So we can expand exponents. Oops. Expand expands. Exponents. I knew I would screw that up. Sometimes my brain just throws in, you know, random thes and ands and whatever. But anyways, hopefully you can figure it out. We can expand exponents onto multiplication and division. For example, one thing that you might want to be able to do is, let's say you have something kind of more sophisticated, like if you have a to the power of 4 divided by b to the power of 6. Okay. You don't have the same base, so you can't, you don't really gain anything by moving that b upstairs, b to the power of 6, by making it b to the negative 6. But what you can do is you can extract a common power, right? So here I can write this as a to the power of 2 times 2, for example. And here I can write b to the power of 2 times 3. So this becomes a to the power of 2 times 2 over b to the power of 2 times 3. So now I can extract that common power of 2. Maybe I'll show it kind of going outside. Oops, that color. So what I'm left with is a squared over b to the 3, and then all in brackets, right? This 2 I've extracted from both of these. And when I bring it back in, squared, or 2 times 2, 2 times 3, I multiply it in. Okay. How about 6? Okay, now I've got a negative exponent. All right, so let's just work out this, this from left to right here. So property 6 says I have a over b, a over b to the negative n. From property 5, I can just bring this negative inside, right? And so I get a to the negative n over b to the negative n. Because I'm dividing, so it only works for multiplication and division, right? But here, this is by property number 5. And I can bring that exponent inside. Then, okay, b to the negative n, right? And there are a couple of ways that you can go about doing this, right? You can rewrite this as 1 over a to the n over 1 over b to the n. Maybe that's a good place for you to start, right? Or you can say, okay, a to the negative n is actually 1 over a to the n. So it's going to get bumped down to the denominator. But then when you have a negative exponent in the denominator, it actually bumps it up to the numerator. But how about we rewrite these as if they're fractions, because that's kind of where we started with this thing. So we have 1 over a to the n over 1 over b to the n. Okay. I've got a fraction over a fraction, so now we're dividing fractions, which means I can just flip and multiply the denominator. Remember from last day? So I have 1 over a to the n times b to the n over 1. Right here, I'm dividing fractions. Now I'm multiplying fractions. So I can just multiply across. 1 times b to the power of n is b to the power of n over a to the n times 1 is a to the n. And then, of course, by, I want to say property number 5. Yeah, that's the division one. Let's see here. By property number 5, I can rewrite a to the power of n over b to the power of n as a over b to the power of n, right? So I can extract it. So this becomes b over a to the power of n by property number 5. So that's how we get to back and forth between these two properties, right? Quite a bit happening between here and here. And then finally, let's see the 7th property. The 7th property says, okay, so now I have different exponents, right? So I have the same situation as in property 6, except now I have different bases and different exponents, right? But it behaves the same way. We just can't collect the same exponent out to the outside, right? And so property 7, right? Notice, right? Different bases and exponents. Oops. So we have a to the negative n over b to the negative n, or m, sorry. If we use the same method that we used here, right, I can rewrite each negative exponent as if it's a fraction, and then I can deal with the fraction. So this becomes 1 over a to the n over 1 over b to the m. Now a little bit faster, right? I've got a fraction over a fraction. I can flip and multiply. And so this becomes 1 over a to the n times b to the m over 1, which is b to the m over a to the n. So just, we need to be so good at just moving back and forth in these exponent laws. Now we've got kind of the rules of the game. So let's do some examples here. We'll come back to scientific notation in a little bit here, but I'm going to go to, because we haven't talked about the roots, the radicals quite yet, so I'm going to hold off on that. But let's talk about these exponents here. So 29 to 34, I'm going to copy that in. Oops. Okay. So first thing you're going to do when you have to simplify an expression and eliminate any negative exponents, well, what I need to look for is, okay, if I have the same base, then I'll be able to combine those exponents. If I don't have the same base, then I won't be able to. So first thing you're going to look for is, do I have the same base? Okay. So here we go. Let's start with 29, all of 29. So 29a, just nice and slow, right? I've got x to the power of 3 times x to the power of 4. So I have the same base. Which means I can rewrite this. I'll write it underneath. I probably should have, here, I'm going to rejig this a little bit. There. So this becomes x to the power of 3 plus 4, right, by property number 1. Okay. So this becomes x to the power of 7. How about b? I've got 2y squared inside the brackets to the power of 3. Now, if you think of 2 as being a and y squared as being b, right, you've got a times b to the power of 3. And I can't remember what property it is. Property 4 says I can expand this power of 3 inside the brackets if I'm multiplying or dividing, right? Multiplying is property 4, dividing is property 5. You don't have to remember the properties. I just want to highlight where everything's coming from. So this I can rewrite as, so consider 2 is a and y squared is b, for example, right? Then you've got a times b and you can bring that exponent inside. So you've got, this has become 2 to the power of 3 and then y squared to the power of 3. But this is exactly like property 4 again, right? And so I'm able to, property 3, it doesn't matter, right? We can just multiply these exponents. So we get 2 to the power of 3 times y to the power of 2 times 3, which is 6. And if you wanted to do 2 times, or 2 to the power of 3 is 8. 8y to the 6th. What about y to the negative 2 times y to the power of 7? Noticing that we have the same base, right? So we can work with that. Y to the negative 2, I want to say, yeah, times y to the power of 7. There are a couple of ways that you can go about doing this, right? But because I've already got the y's on the same level, right? So both in the numerator essentially, then what I'm going to do is I'm going to have y to the negative 2 plus 7, right? If I have the same base, then I can add these exponents, whether they be positive or negative, it doesn't matter, right? Negative 2 plus 7, that's fine. Is y to the power of 5. Okay. Good. Let's do 32b and c. Oops, a is exactly like the one we just did, so that's why I'm just jumping to b. Z to the power of 5 times z to the negative 3 times z to the negative 4. Z to the power of 5, z to the negative 3, z to the negative 4. Let me just make sure. Good. Noticing again that we have the same base, right? And so I'm able to just add all these powers. And it doesn't have to be just two bases, where we can have as many bases being multiplied together as we want, and we can just add these powers and keep going and going and going. Right, and so here, they all have the same base. So it becomes, we can combine these by z to the power of 5 plus -3 plus -4. And if you want to, you can absolutely just do 5 minus 3 minus 4, but I just want to highlight that we are just adding the negative version, right? And so, but that is subtraction, right? You're just adding the negative of it. 5 minus 3 is 2, minus 4 is -2, z to the -2, and then one little holdup is, okay, I needed to eliminate any negative exponents, and now here I've got this negative exponent, but what do? I just move it to the denominator, so I can rewrite this as 1 over z squared. Okay. How about C? I've got y to the power of 7 times y to the power of 0. Remember, anything to the power of 0 is just 1, right? So really, you could rewrite this as 1 over y to the power of 10. Okay, let's write it out. Y to the 7, y to the 0 over y to the 10. Okay. Noticing again here, I've got the same base. So we're able to combine these. And there are a couple of ways that you can go about doing this. For me, I always like to just bring anything from the denominator up to the numerator so that I'm on the same playing field, so to speak, right? And so what I'm going to do is I'm going to bring this y to the 10 upstairs and make it y to the -10. So this becomes y to the 7, y to the 0, y to the -10. Notice here, I'm back to the same format that I had here, right? So now I can just go ahead and add these exponents, right? Because I'm multiplying the same base, and so I add the exponents. So this becomes y to the 7 plus 0 plus -10. So I don't need to waste any time converting this y to the 0 to the power of, or to just to 1, because it's just going to go away anyways. So that's why I didn't do anything here, but I will kind of recall y to the power of 0 is just 1, right? So if you wanted to, you could just do y to the power of 7 times 1 times y to the -10. Nothing changes. 7 minus 10, y to the -3, which of course, if I'm eliminating any negative exponents, I have to rewrite as y to the 1 over y to the 3. Good. Okay. That's the end of our examples there. So, let's talk about scientific notation. So scientific notation you use a lot in chemistry and physics. Usually if you have to denote really, really large numbers or really, really small numbers, and even your calculator will use scientific notation. And it might be a good idea to figure out what scientific notation looks like on your calculator, right? But so in many sciences, we use scientific notation. Surprise, surprise. We use scientific notation to denote very small or very large numbers. Okay. So how it works is you rewrite numbers in terms of powers of 10, right? And so what you have is, for example, if you have 0.0000004, let's say 45, okay? What you do is you move this decimal until you have a value between 0 and 10, not including 10. Okay, so in this case, 4.5. So what you're going to do is you're going to move this decimal over until it's at 4.5. So here, 1, 2, 3, 4, 5, 6, 7. Okay, so here I'll do a little arrow here. This becomes 4.5 times 10, and because I'm moving to in the negative or like in the smaller direction, I should say, our exponent is going to be negative. So 1, 2, 3, 4, 5, 6, 7 to the negative 7. Negative powers for small numbers. Okay, so here, 1, 2, 3, 4, 5, 6, 7. Okay. So what I want you to do is, well, maybe not quite yet, right? Let's do a large number. So the same thing goes for large numbers, except now you're moving this decimal, or you're moving this decimal in the positive direction, or in the kind of larger direction, and so you're going to have a positive power. So for example, if you have 13900000000, I'll count out the zeros in a bit here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 zeros. Okay, so what happens if you have to rewrite this in scientific notation? The decimal is moving from here, right? And what you have to do is you have to go till the numbers between 0 and 9. So here, 1.39 times 10 to the power of, and we'll figure out how many, what the power of 10 is. Now, we're not going to spend a ton of time on scientific notation. I'm going to leave that for when you take a physics course or when you take a chemistry course, and they'll review it again. But it's good to have seen it at least one time. So we'll just kind of do this brief example. We'll just kind of let it be. So here, this is going to move 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so I'm going to just number them out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So this becomes 1.39 times 10 to the power of 13. Okay, so what I want you to do, and I'm just going to bring in that scientific notation blurb here, copy, just so we have it in our notes. But like I said, we're not going to do a ton with it. So, but it's good to recognize it. But what I want you to do on your calculator is type in 1.39 times 10 to the power of 13 and see how it behaves. Okay, so I'm going to go to our Desmos calculator here. So 1.39, oops, I missed one. Not that it's a big deal. 1.39 times 10. And then if I need to raise it to any power, I use this a to the power of b button, and it should step you upstairs to the power of 13. Okay. Notice that here it is just showing it in scientific notation. So that's just an indication that it's too large to fit on the screen. Of course, our screen is large, but usually we max out at 9 digits. So if you have a different calculator, right? What I'm going to do, 1.39 times 10 to the power of 13. And I just want you to see how it behaves, because sometimes it'll have an E, sometimes it'll just have a really subtle space. So just kind of play around with it and see. Or even if you do something, a really large number times another really large number. Oh. So if you do a really large number, 1, 7, 8, 9, 4, 5, 1, 2, 3, 6 times 8, 5, 4, 2, 9, 1, blah, blah, blah. Just doing really large numbers to see, oops, to see what happens here. And here it shows it in nice fancy scientific notation. But if you try on a handheld calculator, you need to be able to recognize scientific notation on your calculator. Try multiplying two very large numbers together on your calculator to help you recognize how your calculator shows scientific notation. How your calculator shows scientific notation. Right. Could be with an E, right? Or even just a space, right? So just know how it shows up. Okay, good. So before we end, let's just talk about roots or radicals, as we were calling them, right? They are radicals. So let's see here. And there's lots more problems for your exponents, right? There's lots more problems. In fact, I should probably have this section switched down here because it includes some radicals. Here, it's just exponents. So you should be able to work through all these problems here. In fact, maybe I'll leave the radicals till next day and we'll just do a couple more exponent problems. How about that? So let's do something like 40A. Right? Do a nice beefy one, right? And so just kind of surveying the scene here, I've got a fraction multiplied by a fraction, which has an exponent on the outside. So first thing I'm going to do is I'm going to, a lot like BEDMAS, right? I'm going to bring this exponent inside, and then I'm going to be able to multiply my fractions. Multiplying fractions, I just smush across, right? So there's a lot going on here, but the goal is simplify each expression and eliminate any negative exponents again. So pretty common question. And like I said, there will be a question like this on test 1 and on the final exam. So another kind of nice one to work through. nice block of problems. X to the 4 times Z to the 2 over 4y to the 5 times 2x to the 3y squared z to the 3 squared. Okay, so what I'm going to do, first things first, I'm going to bring in this power of 2 inside, remembering, so now I've got a combination of multiplication and division, so I am allowed to bring in this power inside, but I have to put that power on every term. So this becomes, rewriting that first one, x to the 4, z to the 2 over 4y to the 5, 2 to the power of 2, x to the 3 times 2, y to the 2 times 2, z to the 3 times 2. Oh, and this doesn't look like a 2, but it will. There. So what I'm going to do is I'm going to simplify these first, right? So it's a little bit cleaner to work with. And then I'll remove these brackets just by smushing things together. So we're just combining all those laws that we spent a lot of time talking about. Here they are, all in play at the same time. So I've got x to the 4, z to the 2, 4y to the 5th. Just leaving that little guy alone for a little bit here. 2 to the 2 is 4, x to the 6th, y to the 4, z to the power of 6. Okay. So now I'm going to multiply these fractions, and I'm slowly inching my equal sign over because I see I need more and more room. And I kind of made this too lofty. Typical thing for me to do. So x to the 4, z to the 2 times 4 times x to the 6th, y to the 4th, over, remember multiplying, you can just multiply across 4, y to the 5, z to the 6th. Okay. What I'm going to do is, well, first things first, I can pull out these numbers, right? 4 over 4, I can actually just cancel. But what I'm going to do is I'm going to pull them to the outside and say 4 over 4, right, times, and then I'm going to have all these variables in a different, because remember, just like up here, when we multiplied these fractions, I can just smush them together. If I'm multiplying, I can pull them apart, right? So I've extracted this 4 over 4, which is just going to simplify to 1, right? And then I've got x to the 4, z to the 2, x to the 6th, y to the 4, over y to the 5th, z to the 6th. To show that these guys are canceling, right? I've got 4 over 4, which is just going to be 1. So this becomes 1. Now I'm kind of doing things side by side here. I'm also going to move this y to the 5 upstairs and the z to the 6 upstairs. So I'm going to do times x to the 4, z to the 2, x to the 6, y to the 4, y to the negative 5, and z to the negative 6. Now what I'm going to do is I'm going to collect all these like bases, right? And so here, maybe I'll use pink for x's, right? X and x. We'll use orange for z, and green for my y's, right? So you're going to collect those. So I'm going to rearrange this first, and then anything times 1 is just itself, right? So now I'm just going to dissolve that 1. You didn't have to write it even. Once you show that 4 over 4 is just 1, you can just ignore that. But I want to show all my steps. for you guys. X to the 4 times x to the 6. Z to the 2 times z to the negative 6. Y to the 4 times y to the negative 5. So now I have the same base of x's, z's, and y's. So now I can collect those exponents. And so what I get here is x to the 4 plus 6, z to the 2 plus negative 6, or if you wanted to, you could just go to 2 minus 6, that's fine. Y to the 4 plus negative 5, but I just want to show where things are coming from. So finally, I get x to the power of 10, z to the 2 minus 6 is negative 4, and y to the 4 minus 5 is negative 1. My last thing I have to do is I want to eliminate these negative exponents, which means I basically just drop them downstairs. The x to the 10 stays up in the numerator. So what I'm left with here is x to the 10 over z to the 4. Make sure that you drop that negative in the power, right? If you have z to the negative 4 in the denominator, that's actually z to the positive 4. Make sure it looks like it's downstairs. And y to the power of 1, usually we just kind of dissolve that, right? Anything to the power of 1 is just itself. How's that? That's a lot, right? But this is what we were building up to, right? Applying all those laws and just kind of working fluently between them and just kind of manipulating until we have something nice and simplified like this. Yeah. Okay, so work through those other problems that are in the notes. Z to the, can you go back to the z to the power of 4? This one here. Oh, so what I was saying, maybe this is what you mean. You want to, if you're moving it downstairs, so to speak, then you want to make sure that you drop that negative, right? Because if you write z to the negative 4 here, then that's actually z to the negative 4, which is positive 4, which is not what you want. So when you move it downstairs, right here, you've basically, when you've got these negative powers all on the same line, you're in the numerator. So when I drop it downstairs, you have to drop the negative. That makes sense. Hopefully. That's right. Yeah, so here, right, going from z to the negative 4, when you drop it down, you have to make it the negative 4 negative, making it positive 4. Awesome. Cool beans. All right. So, like I said, make sure that you work through those problems. Things got big here, right? So make sure that you are able to work through all of these. I know it's not even a lot. I'm not going to pretend like these are a lot of problems. But anyways, so work through those and you've got the solutions, but it's going to be really useful if you're able to kind of work back and forth with exponent laws. Cool. All right. I will see you on Thursday. Okay. See ya. Okay, so if you have joined for business math, what I'm gonna do is